The units of electric flux is coulomb per meter square. The unit of electric field is volts per meter. The unit of electric flux is coulomb per meter square. And when you say electric flux, right, it's again a vector field. Just like how electric field can have an x component, a y component, and a z component, similarly your D can have dx, dy, dz. However, the difference is D is a flux and electric field is a force field, yeah? The force experienced by a unit positive charge. So what do we mean by flux field now? Flux is nothing but amount of a physical quantity that is flowing through a surface. That is what we define as electric flux. So density is per something, right? In this case, electric flux density is flux per unit area. So you know that flux is amount of a particular physical quantity that flows through a surface. And we define electric flux as capital phi. Capital phi. This is small phi. This guy is capital phi. The capital phi E is the measure of how much electric field flows through a given area. So what do we mean by that? Imagine there is an electric field in this direction, pointing, let's say in the x direction, for example, it's just pointing in the x direction. If I consider an area like this rectangular area, I want to find how much of this electric field is flowing through it. First of all, you notice that this electric field is uniform. That means in any point, it's all the same. It's having the same x direction and the same value. Such is called as a uniform electric field. Now, if I want to find the flux of this area, then what I'm going to say is that flux phi E is proportional to the electric field. That means if there's more electric field, then this flux is going to be higher. Not only that, if the area is bigger, then the flux is also going to be higher. There's going to be more electric field flowing through it. So if the area is bigger, it's going to be higher as well. So it's going to be proportional to the area as well as electric field. But the catch is, we want to find, when you say flux, the direction of the electric field flowing perpendicular to the area. So here we have defined this to be my area, that it is the rectangular area. So this guy is the normal vector. Normal vector, that means perpendicular. That means this makes an angle of 90 degrees. This makes an angle of 90 degrees, perpendicular. How do you then find the perpendicular component? You know that the perpendicular component is going to be E cosine theta. If this is theta, this is E, then my E perpendicular is E cosine theta. If this is an E, then this angle is theta, then it's E cosine theta. Now this expression is very familiar to you, right? EA cosine theta, dot products, right? So that is going to be E dot A. So where this A is an area vector, whose magnitude of this vector is the area of this guy, and the direction of the A vector is in the direction of the normal. So A vector will have a magnitude of A and is in the direction of the normal vector. This is normal or perpendicular direction, normal to the surface. I will just show you this visualization. What you see is the flux here. If I increase the electric field strength, my flux also increases. Since the angle is 0, that means the angle between the electric flux and the normal, this guy, what you see here is the normal to the area. The normal to the area is in the same direction as the electric flux. So E dot A is maximum, so which is 51.42, because the area is 1 meter square. If I increase the area to be 2 meters per square, for example, if I just increase it to 1.46, for example, you see that this is going to be this times this, simply this times this, because the angle between the area vector, what is the angle between the area vector, which is this gray one, and the electric field vector? 0. So since it's 0, cosine 0 is 1. So because of that, it's just simply multiplication of this and this. You will notice that it is not only proportional to the electric field, it's not only proportional to the area, but it is also proportional to the cosine of the angle. If I were to change this area, and if I were to make it very flat like this, what will be the electric flux? That means the electric field lines are in the x direction, and I place this, I keep tilting it till the area becomes flat. What will be the flux? 0. Why so? Because the normal vector for this is going to be this guy. The electric field, which I can draw in red, is going to be in this direction. So the angle between them turns out to be 90 degrees. And cosine 90 is 0. So cosine 90 becomes 0. So if the electric field is in this direction, I mean, if you were to take this arrow, the stylus arrow, to be the electric field, if I have my plate, let's say my phone is my plate, if my phone is perpendicular to the direction of the electric field, then I will have the maximum flux. If my phone becomes parallel to the electric field, then the flux through this area is going to be 0. If you have a non-uniform arbitrary area, then what do? If you have an arbitrary surface, I can go ahead and break it up into small surfaces, small little surfaces. Each small little surface is ds. Not only that it has a magnitude, but it also has a direction, always outward, always outward. So this ds is the blue vector here for this vector. This ds is this one. So I can find the d dot ds at every small little ds. I can do the e dot ds at every small little ds. And then I need to add them up together. If you want to add them up together, the small little pieces, you're integrating them, isn't it? So you integrate that over the entire surface. And this entire surface, what is the electric field that is being integrated? That is going to be the electric flux, capital Phi.